now want to move on to the topic of induction, which involves two initial values. So far in all our questions, we've been working with just one initial value. So for example, n equals to 1 or n equals to 0. Now there's a special question which involves two initial values. Can anyone think of a sequence which may have two initial values? Yeah, that's right. There's our Fibonacci numbers, isn't there? So remember with Fibonacci numbers, the first two is 1 and 1, and you need the first two numbers because they add together to give you the third number. And then these two numbers add together to give you the next one, and then so on. So 1 and 1 are actually both your starting values. Does that make sense? Because you don't actually go from 1 to 1, do you? What you're doing is using the relationship between 1 and 1 to give you 2. So therefore, can you imagine if we wanted to prove this, we would not only have to prove the first n equals to 1 and n equals to 2, so the first two values, we would also have to prove the third value, because it's only when we prove the third value that we can prove that yes, that relationship does exist. Because without a third value, you don't actually know what that relationship is. Can you guys see how these two values are actually, they don't mean anything by themselves. You need both of them to form this sequence. You need both of them to start this sequence. So I want you to keep that concept in mind when we have a look at the next question. So in question 6, we want to prove that Tn equals to this. So this is what we want to prove. And we're given that the first term, T1 equals to 3, and we're given that the second term equals to 1. And also that the general formula is Tn equals to 2 times Tn minus 1 plus 3 times Tn minus 2. But remember, this is what we're proving here. So to start off with in step 1, we want to show that it's true for both the n equals to 1 and also n equals to 2 because there's two starting values. So with that, what we know is that the first value we're given equals to 3. So we want to prove using this that it does indeed equal to 3. So we just substitute in T1, and so that becomes 3 to the power of 1 minus 1, which is 0. And this is 1 minus 1, which gives you 0 as well. So essentially you have 1 plus 2 times 1, which equals to 3, which does equal to what the initial value is said to be. So you can say that therefore this is true for n equals to 1. Now similarly for n equals to 2, we substitute in n equals to 2, and that becomes 3 to the power of 2 minus 1, which is 1, and this also becomes 1. So you have 3 minus 2, which equals to 1, which does equal to what we're being told the second term should be. So we can say, therefore, it is true for n equals to 2. Now remember what I said about the Fibonacci numbers? If we have two starting values, then we must work out the next value, so therefore the third value, to show the relationship between those two values. So that means we need to show that it is also true for n equals to 3. And how we do that is we do substitute it into this first. So we have T3 equals to 3 to the power of 3 minus 1, so that's just squared. And this is also squared. So this is 9, and this becomes just 2, so equals to 11. Now, we're not told what T3 is, are we? So we have nothing to compare it to. So therefore, we have to use the general formula to work out what T3 would have been. So by using the general formula, we have T3 is going to equal to 2 times T3 minus 1, so that's why it equals to 2, plus 3 times T3 minus 2, so that's why you have T1 here. We know what T2 is, which is just 1, and T1 is just 3, so we substitute that in. So we have 9 plus 2, which equals to 11. So therefore, we can say it is also true for n equals to 3. So therefore, if true for n equals to 1 and n equals to 2, then it is true for n equals to 3. So can you see what we've done is here we've proven it's true for n equals to 1 and n equals to 2, but we must also use here that n equals to 3 to show the relationship. So we're saying if this does occur, then the relationship between them also makes n equals to 3 true. The other point to note is we've been given the information of the first and second terms, which is why we only need to substitute it in here. But for the third term, we weren't given what it was. So that's why we had to use the general formula to work it out, to compare with this to prove that it's true. Does that make sense? Good. All right, so now we can move on to step 2. So this is our assumption. Now, if there's 2 initial values, how many assumptions are we going to have? Exactly, we're going to need 2 assumptions, aren't we? So we assume it's true for n equals to k, and we want to assume it's also true for n equals to k minus 1. Now, it doesn't matter if you use k minus 1 or k plus 1, because we just want a consecutive number from k. In step 3, we always prove n equals to k plus 1 is true. So you can see that's going to be quite difficult if we have this here already, because you can't prove an assumption. So that's why we've used n equals to k minus 1 just for simplicity's sakes. So that is tk, so n equals to k, equals to this, where we've just substituted in k. And also for tk minus 1, this equals to this here, which is when we've just substituted in k minus 1. So you have k minus 2 there and k minus 2. We have 2 assumptions now, which we have to keep in mind, because if we have 2 assumptions, that means 2 things we need to substitute in later. Assumption is there, so we use it. So we have 2 assumptions, we got to use both of them. None of it is going to be useless. So now we can move on to step 3, where we want to show that it is true for n equals to k plus 1 for this equation over here. So substituting in k plus 1, we have t k plus 1 equals to k plus 1 minus 1 just gives me k, and over here k plus 1 minus 1 gives me k as well. So I want to prove that the left hand side equals to the right hand side. Yes, so the first thing I want to do is start off with the left hand side, and that equals to t k plus 1. And now we use this extra information here. So we're using this information here, and we know this is true because it's told to us. So we can say that tk plus 1 equals to 2 times tk plus 1 minus 1 just gives me k, plus 3 times, and we have k plus 1 minus 2, which gives me k minus 1. So I know the left-hand side does equal to this. You can see we have tk here and tk minus 1, and that should remind you of the 2 assumptions that we had in step 2. So remember how I said if we have 2 assumptions, then we have to use both of them. So that's exactly what I'm doing. So instead of tk, we know that tk equals to this. So I'm just substituting this into here. And here we have tk minus 1. So instead of tk minus 1, I'm just substituting that into there. So I know this looks complicated, but actually all I'm doing is substituting tk for this and then tk minus 1 for that. So all I'm doing is just basic substitution in there. We've used the information as well as our assumptions. We just have to work on manipulating this equation to look like the right hand side. So the first thing I want to do is just expand it. So what I've done here is just 2 times 3 to the power of k minus 1, and then I have 2 times 2 is 4, and this stays the same. And then moving on to the second part of the expansion, 3 times 3 to the power of k minus 2, 3 times 2 is 6 times negative 1. Yeah, so all I've done is just expanded it. I want to simplify some of these things. So remember, always look back to the right hand side, and I want it to look like this. And right now, nothing's really quite looking like that. So what I want to do is make this into 3 to the power of k minus 1, and I want to make that into negative 1 to the power of k minus 1. So I want to make those into common terms with the other one. So how I've done that is from here, where I have 3 times 3 to the power of k minus 2, that's actually 3 to the power of 1. So you have k minus 2 plus 1, which is how I get 3 to the power of k minus 1 there. Can you see that? Good. Now over here, I have plus 6 times negative 1 to the power of k minus 2. And I want to make that into k to the power of negative 1. Now, how am I going to do that? Well, I want you to consider that plus as negative 1 times negative 1, because negative 1 times negative 1 will give us plus, won't it? And that 6, I'll just take out the front there, and I'll have negative 1 to the power of k minus 2 here. So if I consider that this is negative 1 to the power of 1, and if I multiply them, I add the indices, can you see if I multiply those together, that's going to give me negative 1 to the power of minus 2 plus 1. So that's going to give me k minus 1. And this will just leave me with one negative. So that will be negative 6. So can you see how I've gone from this over here to negative 6 times negative 1 to the power of k negative 1? So essentially what I've done is I've used one of these negative ones to multiply into here to increase the index by 1. I've done that. I've just grouped them together. So I've just put the 3k minus 1 together and the negative 1k minus 1 together. And this kind of looks similar to our right hand side, except 3k minus 1 isn't quite that, and neither is k minus 1 quite k. So what I do now is I put them all together. So I put together the common terms. So over here, you can see that 3k minus 1 is common to both of them. What I've done from there is 2 minus 3 to the power of k minus 1 plus 3k minus 1. You can see that these two are common terms. So if I factorize that out, what does that leave me with? That leaves me with 2 for that one. And this has a 1 in front, doesn't it? So that leaves me with 1 there. So that essentially leaves me with 3 times 3k minus 1. So the indices add together to give me 3k, right? So that's how I get the 3k from those two terms over there. Can you see that? All right, well now how do I get this to that? What I've done is firstly, because they're like terms, I can just add them together. So you just have plus 4 minus 6 just gives you minus 2 negative 1 to the power of k minus 1. So that's how I've just made that put together. You can see that this almost looks like this, doesn't it? We're so close. But the difference is this needs to be k, and this here is only k minus 1. So we use the same idea that we did up here, which is consider this negative 2 as a positive 2 times a negative 1. So we have this negative 1 multiplied into this. So if we have 1 up here, we add the indices together so that this just becomes negative 1 to the power of k. And because we've gotten rid of that negative, this just becomes positive. So that's how you get 3k plus 2 bracket negative 1k, which you can see is exactly the same as the right-hand side. So now we've shown that the left-hand side equals the right-hand side. We can say that therefore this statement is true for n equals to k plus 1, and always write our conclusion, which is therefore this is true for all integers of n is greater than 1. Because although we have two starting values, the first value is n equals to 1 and the other value is n equals to 2. So can you see how that's included in this here? So we only need to write n is greater or equal to 1. Just a summary of this, remember this is what we're proving. This is extra information. And because we had two assumptions, we need to sub both of them in, which is what we've done here. And the other trick that we've learned is that we can actually take out the negative, as we've done here, and then multiply it in to increase the index. Just like here, we can make a plus 1 to two negative ones and multiply that in to increase the index.